The Central Processing Unit, or CPU, is often called the brain of a computer. It performs most of the calculations which enable a computer to function. Without a CPU, a computer would be unable to run software or process data. The CPU interprets instructions from programs and executes them. It is fundamental to everything from simple home computers to powerful workstations. CPUs are crucial because they handle all the instructions from hardware and software. Your computer's speed and efficiency largely depend on the CPU. Faster CPUs can execute more instructions per second. This means smoother multitasking and faster processing times. Essentially, the CPU is the heart of the computing device. The importance of CPUs in modern technology cannot be overstated. They are in everything from phones to cars. Any device that performs complex tasks likely has a CPU. Understanding how they work helps us appreciate the power of modern technology. In this essay, we'll dive into the inner workings of a CPU. We'll explain its core components and functions. By the end, you'll have a clear understanding of how this vital piece of technology operates. A CPU is made up of several key components. These include the control unit, Arithmetic Logic Unit, or ALU, registers, and buses. Each of these parts plays a crucial role. Together, they allow the CPU to process and execute instructions. The control unit directs the operation of the processor. It tells the computer's memory, ALU, and input-output devices how to respond to instructions. Think of it as a traffic cop, directing the flow of data within the CPU. It's essential for coordinating the other components. The ALU performs arithmetic and logical operations. It handles basic calculations like addition and subtraction. It also performs logical operations like comparing numbers. Without the ALU, the CPU wouldn't be able to process data or make decisions. Registers are small, fast storage locations within the CPU. They hold data temporarily while it's being processed. Registers are crucial for quick data access. They speed up the processing time significantly. Buses are the communication pathways that connect the different components. They transfer data and instructions between the CPU, memory, and other parts of the computer. Buses ensure that data moves efficiently within the system. The von Neumann architecture is the foundation of most modern computers. Named after mathematician John von Neumann, it describes a system where the CPU, memory, and input-output devices are separate but interconnected. This design allows for the sequential execution of instructions. In von Neumann architecture, both data and instructions are stored in the same memory. This means the CPU can fetch an instruction, decode it, and then execute it. The architecture simplifies the design of the CPU and makes it more flexible. One key feature of the von Neumann architecture is the use of a single bus for both data and instructions. This can lead to a bottleneck, known as the von Neumann bottleneck. Despite this, the architecture remains popular due to its simplicity and efficiency. The control unit, ALU, memory, and input-output devices are all part of this design. The CPU fetches instructions from memory, decodes them, and then executes them. This cycle repeats continuously, allowing the computer to perform complex tasks rapidly. Understanding this architecture helps us appreciate the complexity of modern CPUs. It's a fundamental concept that underpins nearly all current computers. The fetch-decode-execute cycle is the process by which a CPU operates. It's a continuous loop that allows the CPU to process instructions from programs. This cycle is fundamental to the operation of any computer. First, the CPU fetches an instruction from memory. This instruction could be a command to perform a calculation or to transfer data. The control unit retrieves the instruction from the correct memory location. Next, the CPU decodes the instruction. The control unit translates the instruction into a format that the ALU and other components can understand. This step involves breaking down the instruction into smaller parts and determining what needs to be done. After decoding, the CPU executes the instruction. The ALU performs any necessary calculations or logical operations. The results are then stored in the appropriate register or memory location. This cycle repeats continuously. Each cycle consists of fetching, decoding, and executing instructions. The speed at which this cycle is performed determines the performance of the CPU. Faster CPUs can complete more cycles per second, leading to better performance. Section 5. The control unit explained. The control unit is a critical component of the CPU. It directs the operation of the processor. Without it, the CPU wouldn't know how to execute instructions. The control unit retrieves and decodes instructions. It sends signals to the ALU and other parts to carry out instructions. It manages the fetch, decode, execute cycle. It handles timing and control signals. The control unit is essential for the CPU's operation. Section 6. Arithmetic Logic Unit, ALU. The Arithmetic Logic Unit, or ALU, performs calculations. It handles arithmetic operations like addition and subtraction, and logical operations like comparing values. The ALU processes data and makes decisions. The control unit sends data to the ALU for calculations. The ALU performs the operation and sends the result back. This is crucial for tasks from simple math to complex algorithms. The ALU operates on binary data, processing zeros and ones. It can add, subtract, multiply, and divide numbers. It also performs logical operations like AND, OR, and NOT. Modern CPUs often include multiple ALUs for efficiency. Some CPUs have specialized ALUs for tasks like graphics processing. The ALU is vital for running software and processing data. Section 7. Registers and their functions. Registers are small, fast storage locations within the CPU. They hold data temporarily while it's being processed. Registers are crucial for quick data access, significantly speeding up the processing time. There are several types of registers, each with a specific function. Some common types include the accumulator, which holds intermediate results of calculations, and the instruction register, which holds the current instruction being executed. Registers are faster than regular memory. They are located within the CPU, meaning data can be accessed quickly. This speed is essential for the efficient operation of the CPU. Without registers, the CPU would have to retrieve data from slower memory, reducing its performance. Modern CPUs have several registers to handle various tasks. These may include general-purpose registers, which can hold any type of data, and special-purpose registers, which are used for specific functions. The number and type of registers can vary depending on the CPU's design. Registers are a key component of the CPU. They enable quick access to data, improving the efficiency and performance of the processor. Section 8. The role of buses. Buses are the communication pathways that connect the different components of a computer. They transfer data and instructions between the CPU, memory, and other parts of the system. Buses ensure that data moves efficiently within the computer. There are several types of buses in a computer system. The data bus carries data between the CPU and other components. The address bus carries information about where data should be sent or retrieved. The control bus carries control signals from the CPU to other parts of the computer. The width of a bus, or the number of bits it can carry at once, affects the performance of the computer. Wider buses can transfer more data at once, improving the speed and efficiency of the system. Modern CPUs often include wide buses to maximize performance. Buses are essential for the operation of the CPU. They provide the pathways for data and instructions to move within the system. Without buses, the CPU wouldn't be able to communicate with memory or other devices. Understanding the role of buses helps us appreciate the complexity of computer systems. They are a key component that enables the efficient operation of the CPU and other parts of the computer. Section 9. Historical reference, the Z80 CPU. The Z80 CPU, introduced in 1976 by Zilog, is a significant piece of computing history. It was widely used in early personal computers, gaming consoles, and embedded systems. The Z80 is an 8-bit microprocessor, meaning it processes data in 8-bit chunks. The Z80 was popular due to its performance and versatility. It included a rich set of instructions, making it suitable for a wide range of applications. Many early home computers, such as the ZX Spectrum and the TRS-80, used the Z80 CPU. One of the key features of the Z80 was its compatibility with the Intel 8080. This allowed software written for the 8080 to run on the Z80 with minimal changes. This compatibility made the Z80 an attractive choice for many developers. The Z80 also included several advanced features for its time. These included built-in support for interrupts and a powerful set of registers. These features made it a capable and efficient processor, contributing to its widespread adoption. The Z80 is an excellent example of early CPU design. It illustrates the evolution of microprocessors and their impact on the development of personal computing. Section 10. Modern enhancements, multi-core processors, and cache memory. Modern CPUs have several enhancements that improve their performance. Two significant advancements are multi-core processors and cache memory. These technologies enable CPUs to perform more tasks simultaneously and access data more quickly. Multi-core processors include multiple processing units or cores on a single chip. Each core can execute instructions independently, allowing the CPU to perform multiple tasks at once. This parallel processing improves the performance of the CPU, especially for multitasking and complex applications. Cache memory is a small, fast type of memory located within the CPU. It stores frequently accessed data and instructions, allowing the CPU to access them quickly. Cache memory is much faster than regular RAM, reducing the time needed to retrieve data. Modern CPUs often include multiple levels of cache, further enhancing performance. These enhancements have a significant impact on the performance of modern CPUs. Multi-core processors can handle more tasks simultaneously, while cache memory reduces data retrieval times. Together, they enable modern CPUs to perform complex tasks quickly and efficiently. Understanding these advancements helps us appreciate the capabilities of modern CPUs. They represent significant improvements over earlier designs, enabling faster and more efficient computing. Section 11. The evolution of CPUs and their impact on technology. The evolution of CPUs has had a profound impact on technology. From simple 8-bit processors to modern multi-core giants, CPUs have evolved to meet new demands. Over time, CPUs became more powerful and complex, incorporating new features. Multi-core processors and cache memory were significant milestones. Today, CPUs are in a wide range of devices, from smartphones to supercomputers. The evolution of CPUs will continue to shape the technology landscape.